Yes, so I'm Eric. Some of you know me already, for better or worse. I'm working here in the School of Physics and Astronomy. I'm a lecturer in astrophysics, and I'm working on exoplanets in our small exoplanet group within the astrophysics group. And today I'll be giving you a snapshot of what I'm doing relative to the chemistry of these atmospheres. I'm myself a numerical modeler, so I'm only working with computers, but I'm working with all the observers here at the university and around the world, which bring me the data that I use in my computers. So this presentation is entitled "Some Like It Hot." And I'll try to make you understand why we're stuck with hot/warm exoplanets for now, even with the incoming James Webb Telescope. These are the objects we're stuck with understanding and modeling for still a few years. So exoplanets, brand new field, but people have been talking about this for a few times, even from the Greeks. And in the Middle Age, you had Giordano Bruno, who came up with the idea and formulated a bit better of countless planets orbiting countless stars, much similar to our own star. At the time, though, it didn't end up well for people with just such beliefs. Now, if you do study exoplanets at the university, we don't burn you on the forum. Much has improved since. And this graph will display you the state of the field today. So you recognize, hopefully, the planets of our own solar system. Their semi-major axis, meaning the distance between the sun and their average orbit. Depicted as astronomical unit. Perfect. Sorry. And you have the mass of these objects as a function of the mass of the Earth. And you see that our own planet sits at 1 AU at a 1 solar mass. And we have the big planets of the other solar system and some terrestrial planets here. The state of the field today is this. These are all the planets that has been detected and confirmed as of today. And I'm happy to tell you that we've just reached the 4,000 numbers of exoplanets a few days ago. So all these points you see are planets orbiting another star than our own. For some of them, we know their mass. For some of them, we know their radius. That's why you have some radius. The dots have different sizes. Some are only dots. But we have a broad range of planets now to work on. So we have worked for a few years. That's good. And you'll see that these dots are mainly centered on this side of the graph, in the upper left side. So we're dealing with very big, hot, because closed planets. So hence, hot Jupiters. Yep. So why are we only talking about these hot Jupiters? Well, mainly because of the way we are detecting these exoplanets. We don't see them directly because they're immersed in the glare of the star. So we need to detect them indirectly, and mainly by the perturbation they have on their own star. So when you take a planet orbiting around a star, and you see from the Earth, well, you get an eclipse. Not a total eclipse, of course, but you see a dip in the brightness when the planet goes in front of the star. And for a bigger star, of course, the dip is brighter. You have also some gravitational effects, and so the planet, if it's big, triggers a small displacement. And so you get the mass, you get the radius, and you can determine whether it's a high mass, high density planet, such as the Earth, or low density planets, such as Saturn. And you can plot these mass and radius on such a graph, So now we have plenty of points to put, and you see that we find planets with densities as high as 100% iron. So these are big ball of iron. Of course, the highest planets are made mainly of hydrogen and helium, so they are above here on top of the graph. And in between, you can find anything. So you can find our own planet is here, Earth, and you find Venus. You might find Mars somewhere, smaller. They are made of silica. But in between, you find planets made of 100% water, for example. So you really have a physical diversity of exoplanets on all range of densities. Well, if you go back to this diagram, these semi-major axes, you can transform it as an equivalent semi-major axis. Because all these planets orbit different stars, which are not the same luminosity, they don't have the same power emission than our sun. So you can scale that relative to our own sun, get an equivalent semi-major axis, which is directly a link to the temperature of the planet. So what you read here is actually the effective temperature of the planet. So you find, again, these big ball of gas orbiting very close to the stars, or they're very much irradiated by the stars. They're hot, 2,000, 3,000, 4,000 degrees for some of them. And on the other side of the graph, well, you have the cold planets such as the one we have in the solar system, which are very, very cold. So for now, you see that we are very much, due to this observational bias, we are constrained to describe these very hot planets. And the temperature that you get in the bottom here, as a chemist, for me, it's the true parameter to play with to describe these different worlds. The temperature is a key parameter. And so we can start using this temperature parameter to understand the difference of spectral fingerprints that we're starting to get from these planets and compare them to the one we have in the solar system. So the spectra, and thanks to the preceding talk, you had some idea of spectroscopy. While you find the chemical makeup of these different atmospheres, and we do have some of these planets now we know the composition for. And it's linked to one of the techniques, indirect techniques that I presented you, the transits. So if we go back to these transits, it contains actually at high resolution, it contains some idea of the chemical makeup of these atmospheres. Because the light, when the planet goes in front of the star, well, some of its light gets absorbed, some of its light gets transmitted, and when you get an whole spectrum, well, you get absorption lines. And these are really telling you about the fingerprints of your exoplanet atmosphere. So what my fellow colleagues do here at the university, they use instruments to observe these transits in different wavelengths, and they do have the transit depth, the transit brightness is different depending on the opacity of this atmosphere. And you transcribe that as a transit depth curve, and you find all the different fingerprints of molecules in your atmosphere. So it has been applied on a handful of exoplanets so far, and the goal is to, well, of course, have increased this panel. So one of these objects is WASP-19b. As you see, it's orbiting very close to its star, so it's very hot, about 3,000 degrees. And in this atmosphere, with this technique, we've been able to find, well, methane, hydrogen cyanide, and some other exotic compounds that we don't have in such quantity in our atmosphere. For Gliese 2014b, it's a more moderate temperature planet. We have a flat line, so we think that the atmosphere is pretty shallow, and actually is composed of pure water steam. And under this steam, you may find some high pressure, hot ice. So this is one of the water planets I was telling you about on these density plots. And so the search for these chemicals is going on. So recently in the group of astrophysics, one of these compounds has been detected. It's been helium. So it's been detected. It's one of the work of one Exeter PhD student, Jessica Spake. And you see here the spectrum of these transition of helium that they've observed using Hubble. On the hot Jupiter. So basically they've been able to show that this atmosphere was so hot that it was slowly, evaporating in space. And these helium trail, that's what they were able to see in transit using Hubble. So with these spectroscopy techniques applied to transits, we're able now to really go into the chemical details of this atmosphere. So in primary eclipse, when the planet goes in front of the star, you get an idea of chemical compositions, of haziness, cloudiness, and we'll come back to it in a minute. In the phase curve, what you see is how the light of the crescent from the planet is changing when it orbits around the planet. So you get an idea of the chemical composition and its dynamics. And then you have secondary eclipse and direct imaging, which gets you, so that's when the planet, mainly the secondary eclipse, when it gets behind the star, gets you an idea of the temperature structure as well as the chemical composition. So now we have these chemical fingerprints. The observers need modelers, such as myself, to understand where they come from, because when you have at the same time the presence of methane and water, methane of carbon dioxide, well, your atmosphere is obviously in a chemical disequilibrium state. And so you can take your model from a chemical equilibrium, such as the one that people usually use for star physics modeling, but you will not be able to explain how these chemicals exist in your atmosphere. So our goal in the group is to go into and to find all these different sources of chemical disequilibrium. And we mainly doing the photochemistry, so we're interested in the particular reaction rates happening in these atmospheres. We're having a look at the dynamics, how they interact between the two, and of course we do some radiative transfer to transcribe these processes, these physical and chemical processes, into observables. So what we would see if these processes are happening in these atmospheres. And of course, all these processes are coupled, so we are a tight team. And one of our recent subjects has been to incorporate some chemistry from car engines, as Sid mentioned it, to exoplanets, because surprisingly, the conditions in these hot atmospheres are pretty similar to what you have in your car engines. Well, we are hot, we're quite high density, and we're made of hydrocarbons. So it's pretty much what you have in your car engine. And it's the only difference is that we put this car engine around a star. And that is not advisable. And so we benefit from decades of very sophisticated models made in the combustion industry community, of course, where they have had time to develop it and money. But we are able to incorporate these very precise models coming from a huge range of experiments, such as you have here. So we don't do these on site, but I have colleagues all over the world who do these experiments, trying to understand what happens in their car engine, but we take this information and we put that in our model of exoplanet atmospheres. So the next step is to take this chemistry and to couple it with the dynamics, the winds, how one chemical will be transported around the planet. And to do that, we are working with the Metophysics very closely, actually, because some people of the Metophysics are actually working inside our group for 1 day a week, basically. And we are using their very sophisticated model for, well, weather forecasts or climate change, and we're applying it to these strange worlds. So one particularity of these worlds is that they're orbiting so close to the star that they're tidally locked, meaning that they always show the same face to the star. So a bit similarly to the moon and the Earth. The moon is tidally locked to us, and so we always see the same face. But as a consequence, for hot Jupiters, you have one face of the planet that is irradiated and very hot, while the other is always in the shade. And so that creates huge wind around the planet. And we've been able, so this is an image, but taken from results from our coupled models. And it shows that you have a face that is always in the sun and that generates very strong winds to the other side of the planet. These winds have been estimated in our model and verified from observations to be about 5 miles per second. So that's about 10 times the speed of the Concorde. So these are very, very strong winds. And so if you have one chemical in this middle of these winds, it gets transported very efficiently. So, of course, when you're dealing with the chemistry of car engine, you'll get everything nasty that comes with it, and that includes all the soot. So we are not interested in pollution, but, well, we should, but we're interested in the pollution of other worlds. And it's been seen observationally, so this is a recent paper by one of our colleagues here, David Singh, which showed the observations of different spectra of hot Jupiters. And from the top to the bottom, you have an increased haziness and cloudiness. You see that this spectrum gets, you lose some of the information. The sharpness of the peaks decreases when you go to the bottom of this plot. And you have a strange feature appearing here. A slope is increasing, and that is indicative of Rayleigh and scattering in the atmosphere due to the presence of particles in the atmosphere. And so from haze, we can wonder about some other chemicals in the atmosphere, and there are cloud formation too on these exoplanets, and we do model the cloud formation. So we're not talking about water clouds. Due to the temperature, we're talking about molten iron clouds or silica oxide clouds, so glass. So taken into account these very high winds I was telling you about, having this view on these planets, and this is an artist view, of course, well, you'll get little shards of molten iron and glass flying at 5 miles per second in your eyes. So not a good destination. But talking about good destination, you may have heard about these habitable worlds. So when we take a look back at this diagram, these are these blue points here, which sits at a distance from the star where the temperature is, if water exists on this world, well, the water is liquid. We don't know that. So when you hear about habitable worlds in the media, don't always believe it, because we don't get the chemical compositions of these worlds yet. They are too small. We will get there, but we'll still have to wait for a few decades. Even the James Webb Telescope, unless we dedicate the entire mission to observing one of these worlds, we will not know what's inside. And so the goal, of course, is in 1 or 2 decades to go observing one of these habitable worlds and to see the chemical fingerprints for life in the form of methane, oxygen, ozone, such as we have on our planet. And so in the end, I will finish on this plot. Of course, the goal of this research is to find this Earth 2.0. Well, it may be impossible to get there, but at least we'll know that there is a pristine world there that is not screwed by humans. And so this is a picture, this is the ultimate selfie. This is the picture of, it's called the pale blue dot. It's a picture from Voyager when it was in the outskirts of the solar system. And this little dot of blue here is us. And the goal is to transfer these pixels of light into high resolution spectra and to not observe the pale blue dot, but observe another planet in the galaxy. So yeah, stay tuned. You will have to wait for some time though. Thank you.